Should I start?
Sure. I think
Okay,
we are live now, so I see some sort of live screen. That's a
sounds
good sign.
good. So, welcome everyone. I'm really happy to welcome you all to this talk, which is presented by Quantum Formalism Academy. I am the host for this talk. So, I'm Rakvi. I'm currently at University of Maine working in number theory, and we are really happy to have Nima Rasik today from University of Greifswald. Nima is a homotopic theorist, and he'll be talking today about formalization, proving theorems via computers.
All right. Thanks a lot, Rakvi, for this very nice introduction. Yeah. So the goal is to like say something about formalization, about computers, about mathematics, and I guess I'm expecting a very broad audience. So I'm not going to like do a lot of like technical details. I'm not going to expect a lot of like background in either mathematics or like programming or formalization or any of those, but rather I'm trying to give you like an overview of like different aspects and maybe like some kind of like story of like how things developed. And ideally at the end there will also be like lots of sources. And if you're interested, then maybe you can continue one of those or talk to me about it, and we can maybe discuss what else is there to do. So let's kind of like start painting some kind of a broad story about like computers and the world and computers and mathematics specifically. So in some sense, like the way I imagine the role of computers in math is that there was this very old time, like the very past, where like everything was done by hand. There were no electronic devices to help us do anything. And then eventually, starting in the 1940s, 50s, we started to build computers, and they started to do like very rudimentary computations for us and like kind of simplify things. And then in the last couple of decades, we kind of like completely stopped computing anything. Like there's nobody who sits down and compute anything. We have computers, we program them, we write the code, and the computer does it for us. And on the proof side, things have not yet developed as much. So there is some way to do kind of proofs via computers. But we are not as far as just doing computation, just like adding or subtracting. We cannot prove things as efficiently and as easily with computers as we can compute things. But one thing I might wonder is, are we today roughly where maybe computers were in the 1960s, right? So will we look back 30 years from now and think, oh yeah, these people, they had to like prove things by hand and we just use computers to do this. So are we like in this transition phase? And in 2050, everything will be proven kind of using some kind of computational help? Or no, will there be a different trajectory? So this is kind of like a very exciting time where we're exactly in between, and it's not really clear where we're going. So it's a good thing to kind of learn some things about this, learn what formalization is, and maybe get some sense of where this development is heading. Okay, but before we go there, let's start from like very kind of basic stuff. What is a computer? And in some sense, like everybody thinks of a computer as like this device which does stuff for us. But historically speaking, a computer was just a person who computed. And so there were literal human computers who like did necessary computations for us. So examples include like computing prime number decompositions. I mean, just like people would sit down and figure out which prime numbers would multiply to which numbers. Or for example, in astronomy and physics, people computed like stuff based on the data they obtained from certain measurements and experiments. So this is like up until 1950s, this still like existed. And like from the 1950s on, 1940s maybe, we kind of completely gave up on this. And today a computer just means like a device. And so computers have been used in science and in mathematics like quite extensively. Again, like in science, like for example, like an example is like the so-called Harvard computers who would like take like astronomical measurements and like I don't know find information about stars. But this kind of stopped, like I said, 1950s on, where we like use now actual computers. And a good example is like the moon landing, where we could not use people. We really needed to use a device to actually be able to do the computation it takes to like land on the moon. And now today we like so much further. We use computers for everything in science. So like I don't know, for like mathematical modeling and physics, or like AlphaFold is like a nice example of like protein folding in biology and chemistry. But like I want to focus on math because I mean I'm a mathematician. So let's see how computers are used in mathematics already. And right now, like primarily in research math, computers are used in two ways. One prominent way is conjectures. So there's a famous prime number theorem which was conjectured in 1798. And the year 1798 cannot be a coincidence. So if we go back by slides here, we see the year 1797. So it's just 1 year apart. So of course, it's not a coincidence. This conjecture was done based on that table that, okay, there should be a certain behavior of the prime numbers based on the prime number decomposition in that table. And that was then proven like 100 years later. A similar conjecture like this is the one by Birch and Smith and Dyer from the 1960s about it's like a property of like elliptic curves, also something in number theory. And they used like an actual computer. They put in some numbers, they did the math, and some computational like conjecture came out. And it's still open. We still like have no counterexample, but we also have no proof. We just know that the numbers exactly behave the way we want without having any proof that it's actually a correct statement. Another type of application of computers in math is kind of proving something by proving a finite, by like computing a finite number of cases. So the first prominent example of this is so-called four-color theorem. In the four-color theorem, we want to know, can we like take a map and color it with 4 colors so that like no two areas next to each other have the same color. And the way the proof goes is roughly we take an arbitrary map and reduce it with a finite number of cases. And then we check those finite number of cases with a computer. And the computer tells us, yes, you can for those finite numbers. Similarly, there's this Kepler conjecture, which is about like sphere packing. So we have a bunch of spheres in space. We want to know what is the best ideal way to put them in space without wasting any space. And again, the proof involves kind of optimizing along certain parameters and then using a computer to really like figure out optimized solution for this. So in both cases, we first do some like very abstract technical mathematics to reduce to something, and then we use a computer to just compute the last step. So computers already have a lot of applications in mathematics, right? So we conjecture with it, we do compute stuff, and we check finite number of cases. But if you're any familiarity with pure math, then you would know that this is not the main thing that you do. The main thing you do is prove stuff via logical arguments. So what you would want is a way to like do logical arguments in a computer. And so the questions that you can ask yourself is, first, can you do this? Can you prove things with a computer? And the answer is yes. And that's exactly the point of formalization. Another question is, can you automate stuff? Now that if a computer can start proving things, can you automate it? And the answer is yes, to some extent. And then, okay, the last reasonable question is, okay, if you can automate it, can a computer automate like fancy theorems? And that we don't know yet. So it's like, that's kind of where the cutting edge in some sense is. So before I move on to actually discuss what that means, let me actually try to come up with an argument why this is interesting, like why we really want computers to prove things. So depending on who you are, this might already be convincing to you already. Like if you are a kind of a software-minded person or like a student or something, you might not already need any convincing. But if you're in a department and you have any math professors, they might find this convincing. So you can take these arguments and go to your department chair and say, this is the reason why you should, like for a formalization course or something. So already I mentioned we prove certain results by checking computations. But this means that this proof is actually never really checked, right? And so this is both true in these two examples of four-color theorem and Kepler conjecture. You generate a code, and the code kind of reads it's correct, but the code is thousands, if not millions of lines long. So no human being can actually go through the code and check are these computations correct. You just have the end result. There could be a mistake and nobody would know. And so the funny kind of anecdote on this is, so the Kepler conjecture was proven by Hales in 98. And he published it in the Annals. So the Annals is like one of the like most famous journals in mathematics. Originally, when they published it, they wrote a disclaimer that they only have 99% confidence this is correct, because nobody could check the actual details of the proof. So nobody knew. Like nobody said it's wrong, but nobody could actually check the millions of lines. So eventually, Hales himself put together a team and presented a formalization of this result using these kind of like formalization mechanism to formally verify this has to be correct. So this was just recently, like 2015, not that long ago. Similarly, the four-color theorem was also formalized earlier in 2005. So now both of these have very careful computer-checked proofs that we know exactly behave the way we want. Another reason is math is hard. It turns out it's not just hard for you if you're just learning math, it's hard for even the smartest people on the planet, right? So the two examples that we can give here is one is like Vladimir Vygotsky, who was like a famous mathematician. He did a lot of work in like derived geometry and high category theory and like very advanced mathematics, and he got a Fields Medal for this work. And one of the theories he proved is the so-called homotopy hypothesis. It doesn't really matter what it is. The point is he published a paper in 91. And then 7 years later, some guy, Simpson, came up with a counterexample without ever finding a mistake in the original paper. So in 98, there were like two papers that were opposite of each other, and like none of the two had any mistakes. And eventually a mistake was found in the first one many years later. And in that whole time, nobody ever kind of criticized it. Nobody said this is wrong. And so this is like for Vygotsky, this was a very kind of disturbing experience that like you can write a very kind of fancy paper, publish it in a good journal, and has this mistake and nobody knows. And so he wrote kind of like a very kind of like a summary of his thought process throughout this time, which is like I cited here below, and it's a great read. It's like super easy to read. You don't need to know any math. It's like more of the story of what he experienced. And as part of this text, he has this very nice sentence, which is like a technical argument by a trusted author, which is hard to check and looks similar to arguments known to be correct, is hardly ever checked in detail. And this is like very true. Like this is like a very true experience in like very advanced research math, that some of these like tiny details might be ignored in some of the stuff. And so that's exactly motivated Vygotsky to look into formalization as a way to kind of make sure all the details fit, and like the computer is checking the kind of arguments that we are presenting on paper. Another example is this so-called condensed mathematics. So this was introduced by Peter Scholze. He is also a very kind of famous mathematician in Bonn. He has also won a Fields Medal for his work. And he himself proved a result that he wasn't sure it's correct. He didn't say it's wrong, but he also didn't know it's true per se. It's like very disturbing, right? So he was at the top of his field. He has this very complicated result. There's not that many people who can even check it, but he needs it for all the other stuff that he wants to do. So now he's kind of stuck. So what Scholze then did is he went online and said, please, can some people try to formalize this in a proof assistant and see if it's actually correct? And that led to the so-called liquid tensor experiment, which actually formalized it in Lean 3 a couple of years ago. And so this was a kind of very interesting experience where like formalization can help a very kind of advanced research mathematician kind of gain certainty that what they're doing makes sense. So this is like the summary of these two is even the top minds of the world can either make mistakes or not make mistakes, but not be certain that what they're doing is correct. And so this means this applies to everybody else as well. And so formalization is a good way to kind of counter this. Another issue is that's actually very positive in some way. There's more math than ever. So there's more mathematicians. Math has become way more global. It's like all over the world, there are people doing mathematics now. This is great, but this also means nobody knows everything. Nobody knows all the people, all the universities. We're like very much losing oversight. And this is exactly like a computer is, if there's one good for one thing, it's taking in a ton of data and doing something with it, right? This is like the whole point. So doing mathematics and proofs and mathematical proofs in computer exactly can benefit from this gigantic input of mathematicians and mathematical papers. And so, of course, finally, that one thing that everybody's excited about these days is some kind of AI, machine learning. And ideally, you would want some sort of way to like prove mathematics using AI. But the problem is standard LLM ways, they're just like have hallucinations. So here, of course, I mean, I tried on purpose to give it some statements that it would hallucinate about. So just standard ChatGPT. I asked it to give a proof about something that's clearly false, and actually gave me a proof, which like is clearly not correct, although it has the right words. Now you might say, okay, more further advanced models will do better, and that's absolutely correct. On the other hand, if I give it a statement for a complicated proof, and it comes out with a proof which is like, I don't know, 1,200 pages long, nobody could say for certain there's no mistake in there. Like there's just, as far as I know, there's like no solution to these hallucination problems. Right? You can like make them better, but you cannot guarantee they go away. But in some sense, and so I'll try to discuss it a little bit in the second half, formalization kind of takes care of that. You cannot even make a mistake. Like if the statement is correct, you can then run AI algorithms there, and the product outcome will be definitely correct. And a kind of interesting result that happened like I think a year ago now or 2 years is this kind of work by Google DeepMind, But since then, we have also seen various other people try to like prove mathematics by combined formalization and like machine learning methods. Okay, so this is kind of a first, like a half of the talk. One could say, what is the point? Computers are kind of useful; they're everywhere. You want to use them to prove mathematics. There's many reasons, at least for why you want to use it to prove mathematics. And so the goal now is to see what is formalization and how can we use it and how can it help us like prove stuff about math. So now is a good time to like take a short break for like a couple of seconds. If there are any kind of questions about this, I mean, I didn't really say anything like too crazy, so maybe not. But if there are any questions, then now it's a good time. Otherwise, I move on.
So there is a question in comments about Google DeepMind. So the
Aha.
question is the apparently correct Google DeepMind proof, was it just another LLM or it was an assistant proof? Yeah.
Aha. So I don't know all the details, but my understanding of this is that they use this the programming like the proof assistant Lean. And so what they did is they developed an algorithm which kind of like auto formalizes, so to speak. So I think you by hand, so you use, I mean, this like, so I'm taking this example here. This is the statement written like human language. You by hand translate it into a statement that is in Lean. And then you get up to here, and then what should happen after this next step is the proof. So then like by, and then there should be like a proof. And this you feed into your LLM algorithm, which has kind of like input statements. And what the AI tries to do is to kind of find a proof for this. So by step trying some methods, making mistakes, then going back a couple of steps, trying some other method until you actually find a complete proof of the statement. So the kind of the AI part, the ML part is on like Lean code, so to speak. Like what kind of method, what kind of steps in Lean allow you to go from one proof step to the next, and so on until you can get to an end, roughly speaking. I don't know. Did that answer the question, or? That's a great question, though. It's good.
So the questions are welcome at any time. Yes.
Sorry?
And I was just saying the questions are welcome at any time. So
Yes, indeed.
please, yeah,
Questions are welcome
please,
anytime.
please feel free to type as many questions as you have.
Yes, I cannot promise I can answer them, but I'm happy to try. Okay, then let's actually try to actually say something about formalization as a thing. So I will, like I said, I will not want to assume that you all know what like a lot of math. So I try to keep the math simple. So, but this might also be boring to some people who are like very advanced. So let's see if I can find a balance here. So what is formalization about? Roughly speaking, what I'm doing is I start with some sort of mathematical statement, some sentence in math. I kind of translated it some kind of in a language that a computer can understand, so the so-called type theory. And then I choose a programming language where I can enter this type theory. And then in the programming language, after it's entered, I can in some sense formally verify it. So an example is, here's a sentence, every bijective function is injective. This is a statement in math. If I hope this is like not too hardcore. If you don't know, it's just bijective and injective are like properties about functions. And this is actually true. So it is being bijective is a special case of injective. And I might like translate this into type theory using this kind of like notation. So here is bij or bij f is in some sense like saying some sort of, this is bijective. And then I can write this, for example, in Lean using the following. So there's a specific syntax in Lean that allows me to kind of like write this in Lean. And like the formal verification is that there's some kind of type checking happening in the background. So let's try to like explain these steps in more detail. And this helps going back to like standard proof statements in math. So how does proving in math works? There's in some sense the math, so there's like mathematical objects, there's sets, there's functions, there's groups, there's topological spaces, and so on. And then there is the logic. There's like formulas, there's sentences, there's like proof steps. So if, then blah. For and, I prove it like this. For or, I prove it like this. And every bachelor in math has some kind of course where they teach you how to do with this. So in some sense, in standard math, the way we do it, mathematics and statements about it live in two separate worlds. So for example, if I write this sentence, let f from a to b be a function, if f is bijective, then f is injective, then some of these are like logical words and some of these are like math words. So like injective and bijective are math words. If then is something like a logical thing. So this is not good because the computer doesn't have like a true understanding. There's just code. So I need to put all of it into like one level. And the way one good way to do this is so-called type theory. So in type theory, we have like types. And so types are in some sense at the same time our sets, like so our kind of objects, but also our propositions, so our kind of mathematical statements. And then, so for example, a function in this setting, so if there's a function type, is a function in the usual sense, but it also encodes implication. So if I want to have an implication in this setting, what I do is I look at a function. And then there's like funny examples like equality types. So they will get to this example. So then in type theory, how would I then prove something? I change my perspective. If I want to prove some kind of implication, I construct a function. So in type theory, the way I would prove this is I would say I need to construct two types. So the type that when element in it encodes being bijective, a type when element in it encodes being injective. And then what I need to construct a function which takes a pair f alpha to some kind of pair f alpha prime. So this is kind of like a proof is now a function that assigns like the thing, the info that I have to the info that I want. And so now this I can really encode into a computer because computers know how to do with functions and types and so on. But I cannot use any programming language I want, right? So here it kind of matters. So I assume like almost everybody is familiar with Python, it's like kind of C, Java, this kind of stuff. But what I really need in this setting are so-called strongly typed static programming languages. So I really need like the type, like everything needs to have a type, and the type needs to be very static and fixed. And I cannot like change around all it. Like this makes it somewhat inconvenient to use for like a beginner. Like if you're like programming for the first time in your life, this might be like somewhat more difficult and technical. But it is exactly what you need to encode mathematics, because in mathematics you cannot just change the type of stuff around. It really matters that a specific type encodes a specific proof statement that cannot just change. And so the examples, the prominent examples of this are things like Lean, Acta, Coq. These are like very prominent programming languages which are used to formalize mathematics already. Okay, so now let's look at an example. So this is Lean code. The first lines are like very standard. So for example, I can define n. So n is 3. Like n is a variable, just 3, nothing special. But here, notice I explicitly say n is a natural number. For example, m I can write as 2 plus 2, also very basic. I can check n, and so Lean then knows that n is a natural number. I can evaluate, right? It's very basic, like in any programming language. I can evaluate m, and it will evaluate to 4, because 2 plus 2 is 4. I can also define strings. I can define functions. So here I could just say, here's a function plus 1 from, and so now here change the notation. Here was n in this, but this not is the same as n, which just takes an element n to n plus 1. So this is like standard lambda notation, so to speak. And now I can, like, for example, evaluate plus 1 of n. So n was 3. So 3 plus 1 is indeed 4. The world is still good. But now here's a funny thing, right? If I try to evaluate plus 1 of m, it will complain, application type mismatch. Because m is an integer, and plus 1 has domain natural numbers. And this will not change. Like it will say this type, the input type does not match with the input type, the domain of your function. That's a no-no. It doesn't work. And it's exactly that type checking that makes proofs in this setting work. So let's go slightly more fancy. So one thing I can do here that I can, for example, not do in so many programming languages, I can define the type of identities. So if I, let's say A and B are two natural numbers, then I can say I have an egg, that's an egg is something in the type of identity. So it's telling me that A is equal to B. There's a variable and something I assign to this. And now I can start like prove very basic stuff. So for example, I can like define this function flipped, which has input equality, A is equal to B, and the output is B is equal to A. So this, in standard math, we would think of this as being implication. But like if A is equal to B, then B is equal to A. But Lean just thinks of it as a function. So there's just a function where the domain is A equal B, and the codomain is B equal A. That's all it is. And so if I have defined it, then I can, for example, put in stuff. So I can plug in now A and B and egg. And what I would expect is an element in B equals A, which indeed it is. So flipped A, B, egg is exactly an element in the codomain of the function. But this is how a proof works. So a proof works by providing the input and then getting the output as an element. Now, even more abstract, I can sometimes start in let's say Python or whatever. I would usually have types like natural numbers and strings and I don't know lists and so on. But here in this setting, I also have just a type of types where like this is in the analog of our sets. So there's like no structure to it in some sense. There's just like an arbitrary type just floating around that I can use to like then bootstrap my additional structure that is the standard way I do mathematics. So for example, if I take X to be some kind of type, then I can define what is called com group. So it's a commutative group, usually called abelian group. And so now this is saying I have a set X in addition with the commutative group structure. And now I can like prove very like basic results, like every commutative group is a group. And how do I prove this? I just I start with a type G. I start with information that I know it's a commutative group. And what I have to extract from this is the data of a group in G. And there's like there's a proof argument that there's a function that does that. And this is exactly where the type checking happens. So the type checking of the proof term ensures correctness. If I write these first two lines correctly, so if I get to this equal sign here, everything I write, as long as in the end Lean tells me that the steps assemble to an element in group G, is okay. It could be one line, like I wrote one line here to finish the proof. I could write 5,000 lines. If in the end I have some sort of element in group G, I have a proof of a group of a G with a group structure. So there's no room for error in some sense. Like modulo, some very technical kind of programming issues, if there's a kernel issue or something, there's no issue that arises at this level anymore. So that's exactly how you can also, and as we will discuss later, this is exactly how AI algorithms can benefit. As long as the statement up to here is correct, you can then run an AI algorithm on this. If it comes up with a solution, it will be correct. And I don't have to worry about hallucinations or mistakes or anything like this that can happen in LLM setting. Okay. If it's so easy, then why is not all of math yet formalized? Which is, I kind of mentioned already. Well, there's a lot of mathematics. There's just like in some sense, like one fundamental reason is you need to like formalize everything from scratch, from like 5,000 DC up until today, and there's a lot of it, and people are working on this, but it takes a lot of time. Another problem is a lot of math papers have slight and subtle imprecisions in how they deal with proofs. And proof assistants are just very picky about this. And if you actually want to formalize it, you have to be very careful and like backfill all the details. And that can take a lot of time and energy. And sometimes when you formalize stuff, some papers and some math research use different foundations. You have to kind of make sure the foundation matches up with the proof assistant that you're using. So there's kind of at least these issues that slow things down and make it hard to kind of formalize all of math. But it is progressing. And ideally, it should work out with some reasonable timeline.
Can I ask a question at this point?
Yes, of course.
So in the previous slide, you mentioned that about this thing, right? That every commutative group is a group. We can check that.
Yes.
So is it like more like does it work in generality? So the idea here essentially is recognizing if something is a subset, right? And then identifying smaller set as a like something in smaller
Yeah,
set
in this
as a member
case,
of a superset.
yes.
So
This of course is a very, very simple example. Like there are much more, but yeah, in
yeah,
this
yeah,
case,
no, no.
it's basically just
Okay.
looking at the commutative group is a group plus some kind of extra commutativity structure.
Right, right,
And this map is just forgetting the commutativity, just remembering
right,
the rest of the group structure. That's exactly the proof. Yes.
right. So can we like also like enter like subsets and like ask whether it recognizes member of subsets as supersets? So something like that.
Yes, I mean you can define injections,
Okay,
right? There's like injections. So this is an injection exactly, and so this is saying that like there's something like from com
right.
group to group there's an injection which
Hmm.
forgets the commutativity structure, so to speak. I
Yep.
don't, is it an injection? There's a map. I don't know if it's an injection actually because there could be different. No, it should be an injection. No, it's fine. Yes.
It's an
If
injection.
it's commutative, then it's uniquely commutative. So yes, that's an injection. But
It's
then there's also a map from group X to just X. And that would not be an injection because one type
right.
can have many group structures. Yes,
You
that's
can
true.
have many group structures. Yeah.
Yeah.
Yeah. That's
But you can always forget down to type, so to speak. So just to the bare set without any other information.
true.
Okay,
Thank
does
you.
that answer your question? Or
Yeah, yeah, thank you.
yeah, so exactly. So there's progress in this direction, but it's somewhat slow for now. Despite that, a lot of really cool projects have been worked on. So there is active, like very kind of advanced research mathematics that has been formalized or is being formalized currently. This is in no means an exhaustive list. I'm just like picked from some areas in mathematics, like number theory, analysis, algebra, and so on. Picked some examples of what people have done. And so yeah, so this is like if they have any interest in any area of mathematics, you're more than welcome to like check out the area that interests you and like check out what's being formalized in there. So there's this. I think there's nothing left in math where there isn't some effort to like formalize it these days with some proof assistant. Okay. Given that, like, I expect there to be in given like this is the event might have some people interested in like machine learning. So I thought I mentioned some AI or semi AI aspects of formalization that with like, and I break it down into three things. So there's like the basics. So there's like the stuff that is already completely standard in formalization these days, the stuff that is cutting edge, and towards the end, I might also mention the dream where we're trying to get to in hopefully in the next years or maybe decade or so. So there are several basic things that proof assistants already do, which are could be considered intelligent or maybe semi-intelligent or whatever. So let me mention there's several of them, but I picked out three. You think that like easy to convey and like interesting to know. So the first one is interactivity. So this picture is kind of small because I need to fit several things on one slide. But the word that to focus on here is the word one goal. That's really the one that matters. So one thing that the proof assistants do now, like not all of them, but especially Lean does this, Quark does this as well, is this feature of interactivity, where like I kind of prove things, and there's in some sense like a tactic state, keeping track of all the assumptions I have and all the goals that are left. So it's kind of telling me what I need to prove. So in this case, I just started with the proof. So there's one goal. It's like the result itself. But then as the second I apply one step, so I make one step into the proof and I write something, the kind of tactic stack recognizes this and tells me, okay, now you made one step, so you brought down the goal into two goals. So in this particular case, I did an if and only if statement, and I made some kind of move, and this breaks down my if and only if into two ifs, so into two directions. And so wherever like I keep progressing with the proof, it kind of tells me always, okay, where am I, what is left, what assumptions do I have, and what do I have to prove. So like, this is like very nice features for very long and complicated proofs that I don't have to keep track myself. The computer tell me what's going on. And so you can kind of progress and continue until you see somewhere in the top, it will say no goals if you're doing things right. So if you get to the no goals, that means you did it right and you're done. You've completed the proof. This is also exactly how computers can kind of formalize stuff. That's how they work. You need to something like that. They start formalizing stuff. They kind of try moves and they ideally try to get to this no goals situation. That's kind of how like an AI would formalize a proof. So interactivity is kind of very useful for somebody who's just starting with formalization, as well as for like experts trying to formalize very complicated results. The other one is implicit arguments. So one feature that a lot of these proof assistants have is the ability to recognize what the input should be based on the kind of background data. So here, this is the proof that we already mentioned. It's a very simple example. Every commutative group is a group. And here, my input was like this G and alpha, where alpha is the commutative group structure. And one thing I can do is I can just like remove the alpha, right? So I can just remove the alpha here and I put an underscore. And the computer will check, realize, okay, what do I need here? So what is the input that I require? It's a commutative group element. So I can look then here and really see, aha, there's one here. So I just see it, I match these two, and I'm done. I don't complain. Even more, you can just like forget even the G, right? So it will know, what I want some sort of type. And then I look here, aha, I see top, there's a G of type, so I'm good. I don't have any worries. Now, this is not very impressive. You might say, okay, who cares? It's just like it's to just put these variables in. It's like easy, and you would be absolutely right. But like, of course, things always get more complicated in life. And so this is an example in Coq, which is another proof assistant, but also has this implicit feature. And so this is very small because it's very long, but it's like a formalization of what's called double categories, which are like this kind of technical thing in mathematics that I was involved with. And the double category involves a ton of data. You really do not want to keep track of all the variables. And so you can see here, there's all these like lines on now next to each other. This is all like implicit stuff that's being taken care of. So here or like here in the bottom as well, there's like maybe 8 or 10 of those. But like the proof assistant, it just keep tracks of those, and like nobody has to worry about it anymore. Like you being imprecise on your side, but the proof assistant is taking care of that, is making sure that every one of these underscores is very precisely determined. And there's no like imprecision or no kind of, no detail is left unchecked. Last thing I want to mention are tactics. So a tactic is in some sense a proof step that allows us to go from one step of the proof to the next. And so there are like very basic tactics. So for example, here I have this proof that is kind of showing me how propositions, how they interact with and or. So if that's familiar to you, but if not, it doesn't really matter. What matters is the tactics, such as apply and intro, allow me to use standard like mathematical arguments, just like introducing a variable or like deducing a step from a previous one. But then there's like more and more refined tactics, which are like very much like the more advanced they get, the more AI they become in some sense. So one thing that's kind of like in Lean, for example, we can try is the so-called simp. And so simp will kind of you can kind of like do simp and like some kind of statements, and then it will try to deduce the result that you want by like filling in the assumptions. So if you write simp only, it will kind of like try to like prove the desired result from these assumptions. And you in fact can't even do something different. So here, if you look, I have like the simp only, and I have like 5 assumptions that are necessary to finish the simp only. And I left here, I have the last one is this thing called or true. And here I tried the same thing again, but left the or true out. And so let's say I didn't know. One thing I can then do is I can try the so-called simp question mark. And then simp question mark will look at the proof that I have and then tell me, okay, what step should you try to complete the proof? So it is telling me then try this, simp only or true. Like it's exactly recognizing which steps of the proof are still missing and what would be the next step you would need to complete the proof. So there's some kind of underlying mechanism in behind the scenes, which is kind of telling simp what are reasonable steps to complete a proof. Doesn't always work, but it can be quite helpful for like these kind of basic manipulations. A more refined version is so-called ASOP. So if you try ASOP, it would just close the whole thing. So ASOP is really kind of doing some kind of weighted graph search in the background. Like there's specific steps it can take. And so ASOP it's a very advanced system which tries to prove things by exactly. So checking is something like proof trees in some kind of automated way. Yes. So this is kind of these 3 are like very standard. So like tactics, implicit arguments, the kind of things are like everyday use by all proofs, like by kind of formalizers all the time. What's somewhat more fancy than this is like formalization in machine learning in a more literal sense. So the kind of what people have been doing is that you start with a proof assistant, let's say Lean. You start with like a set of established results, and then you try to run some kind of machine learning algorithm on this, and like you kind of feed this information and try to like extract more and more results from this. And ideally, you want to prove some kind of fancy result at the end. So I already mentioned alpha proof, so that was for Google DeepMind, but a bunch of other people have worked on this. So there's a Gödel prover, there's also DeepSeek prover from DeepSeek. And there's also now this kind of Lean Copilot, which is like a version of like GitHub Copilot in some sense, which has kind of more refined tactics, which also does some kind of machine learning methods to like complete proofs. So this is kind of like I would say the cutting edge, which is not really usable in general for everything, but it's clearly something that's coming. Where like if you have enough input statements, enough input kind of like lemmas and theorems in your proof assistant, you can then start kind of proving more and more advanced results, and ideally get to something that is like new or interesting. So it's like not yet there, but getting there. The dream, in some sense, is to automate also the first step. So coming back to this pipeline from math to kind of formally verified statements, what we discussed mostly in the ML side is to get it from step like 2 to 3. So and sometimes like if you input the statement in lean or whatever, and then it tries to prove it automatically. What we haven't discussed is from step 1 to 2. Like if you have some kind of mathematical statement written in a paper, can you extract a code out of it? So this, in terms of this, called like natural language processing. So you have like in a natural human language written sentence, you want a code that corresponds like correctly to that natural language sentence. That I think is like very much work in progress. I don't know. People have some projections, and this could be done in the coming years. I don't know. But I would say right now this is like rather a work in progress. But if you could do also this step 1, then I mean there's nothing holding up. You could just start taking all the papers, putting it into the system. The system would like formalize them, and then you also like use ML on this kind of like output code, and then can prove more and more results. So that then would become like a kind of cascade of more and more results every day. That would be like a very exciting result, but we'll see. So right now, people are working on like natural language processing, for example. It's like this Lean 8 or like Lean Workbook, where they're trying to do some of the stuff. I think there are also probably other groups, but just 2 examples are these. So yeah, this is kind of like the dream. Let's see how far we are in like 5 or 10 years from now. Maybe in 5 years the dream is already done. Maybe it turns out it's like very unlikely to happen anytime soon. We'll see. Let's say any of this sounded remotely interesting and you would like to like try some stuff out, then here are some steps that you could consider. I hope some of them are useful. So one easy thing you could try is a natural number game, which is like online. It just gives you like a very basic intro to Lean through a game. It's called a natural number game. If you're more committed, you can actually locally install Lean. It's like super easy. And then try some of the like material that helps you learn. So there's glimpse of Lean, which in a couple hours gives you some intro. Mathematics in Lean is somewhat more advanced. There's a lot of talks online. And there's, if you like really into functional programming, you can actually also do like completely advanced functional programming in Lean, devoid of any math. You don't have to do any math in Lean if you don't want to. But yeah, there's like a lot of resources now, talks and so on, to like learn a little bit more about how formalization is kind of changing mathematics. So here's some sources that you can use, but there are, of course, also others. And yeah, with that, thank you for your time. If you have questions, I'm more than happy to discuss and answer.
I think there are a couple of questions here. So, first question was, is there any comment on Russell and Whitehead's formalization of arithmetic and its eventual translation into the Coq language? This took several years, if George recalls correctly.
I don't have any particular comment right now. I believe that. I don't know every single project, formalization project out there. So, but Russell, this sounds right to me. But I honestly don't know. I mean, in Cork, the stuff that I know, yeah. I mean, I know other formalization, but no, this one I don't know. So I don't have any particular comment on this. Sorry.
Yeah, so yeah, before I take any more questions, let's thank Nima collectively for this great talk. And yeah. I'm trying to look if there are any clap emojis, but I can't find it. All right, I think there is another question about, so can you explain strong, weak, and static part of the coordinate axis?
Yeah, so I'm myself not an expert on this myself, so but I will try. So roughly speaking, like so there's static and dynamic like type, so like typing, which is telling me okay, like how predetermined is the type of everything. So does a type is like kind of like is a type weakly determined when I define a variable, or it's like very strongly determined in some sense. So if a Python, for example, I would just write n equals 5 or something, and I just start coding, or I would say x equals like I don't know. But then if I write n equals 5, and then the next line I write n plus 3.2, then what the computer will do, it will automatically make my 5, which probably was some kind of integer or natural number, into a double, and then add it with 3.2. But it automatically translates, it just deduces the reasonable kind of type what it should be. So it's like, no, so that's exactly, it's like, so Python is here, for example, if you look in this diagram. So it's like very dynamic. It's not very statically determined, the type. So this is like, and strong and weak is saying, okay, like how strictly does it need everything have a type in the first place? So for example, like, yeah, so to like distinguish, for example, Python in Haskell, Haskell is like both of them have types and everything has a type in some sense, but Python can change it kind of reasonably easily, whereas like in Haskell, it would be like very strictly enforced. Whatever type you choose in the beginning, you have to stick to it. Whereas for some programming languages, you don't even need to have types at all. You just like, so it's C, I think is next time. Exactly. So C is here in the weak side. So you don't need to even think about types. But if you have them, like they will be also statically enforced. So this is like roughly speaking the kind of the picture. But yeah, I'm not like a software developer like primarily. So this is like my overall understanding.
So I think there is a similar question.
Uh-huh.
So you already mentioned some, but specifically, let's say if you want to compare Coq with Lean, then
Uh-huh.
what are some strengths of Coq when we compare it to Lean, or vice versa?
Yeah, I think I think at the high level they're like very similar. So they're both interactive. Uh, so what is it? So I think the difference is this, like, I don't know if that's counted as high level. It's somewhat more technical. It's like the core kernel is bigger. So the center and subset of the programming language that actually does the type checking in the background for Cog is larger than Lean, as far as I know.
Hmm.
Um, on the more concrete side, the difference between Lean and Cog on math is that for Lean, there's one central library, mathlib, which has kind of that's so the people who use Lean, like there are more libraries than this, but people who use Lean try to actually get everything into mathlib. And the center is to have this one library which has all the central results. In Cog, there is no such central library out there. There's no analog to mathlib. And so there's different libraries focused on different aspects of mathematics. And they do not share one kind of base library that they all kind of fall back to. So this is like more on a concrete level. It's different, but this is like more of a design. This has nothing to do with the programming language. It's just, I think, a choice of the developers, I would say. There's no, like, as far as I know, there's no reason that this has to be like this. Um, yeah, other than that, I think these two are like by far the most similar to each other. Like they have a lot of similarities on a, like on the first step, which is also why I find these two easiest to use for myself, I would say.
And I think there was one question towards the end of your talk. The
Mhm.
question says, "What about mathematical conjectures?" So
What,
I
uh, what about? What is the question in more
what
detail, maybe?
Yeah, it's just a question. Maybe
So at the
Michael,
end, so
if you would like to explain or your question a bit, that would be awesome. Or I
maybe
guess the
the
question is more about maybe if we can some sort of, I don't know, try to code mathematical conjectures into Lean or something and try to figure out if like what its response is as a proof. I don't know, I'm just guessing.
yeah. So this is exactly what to my understanding, this is like not yet possible, or at least not in a like big way. But I don't think there's any technical barrier. It's just like it hasn't been. This is exactly, I think, what we're aiming for here, right? So this is the next step:
Hmm.
is you feed some known stuff, some known results, and then exactly you want to fill in the statement. So this is
Yep.
basically what these people are doing, right? So the DeepMind people, they did this with like math Olympiad questions, for example. These are not
Yep.
conjectures, but they were conjectures from the proof assistance point of view, right? So you
Hmm.
will only gave some basic statements. You gave them this Olympiad question, said, "Can you prove it?" So the fact that it can prove it means that the computer proved something that it itself didn't know.
Hmm.
Um, that's not what we want. What we really eventually want is pick some fancy conjecture and try to prove it using the proof assistant. Um, that's uh, that's hard for now because also a lot of the mathematical conjectures need also a lot of basic like background mathematics that hasn't formalized yet. So you have to maybe get closer to like research. I've seen the question now. It says, are computers making their own conjectures? Uh, I don't know if that is something people are working on. That could be. It would make. I think the problem for making having computers make conjectures is that theoretically in math you could make a lot of sentences. Like there's a lot of logical sentences that are out there, but the math community makes very conscious choices, which problems we care about and which we don't. And there's some intuition that goes into it. There's not like some naive, like anything that is not proven is interesting and people should prove it. There's some very deliberate kind of like community kind of decisions that this is an important conjecture that we should prove because it gives us some insight. And that part, I don't know if that's like yet possible for a computer to make a conjecture that would be actually interesting. So I'm not aware of such an example. I mean, I would not say it's not possible. I just have not seen it. Yes. Aha, I may have missed your introduction. Can you share about your background? Yes, I didn't say anything about my background. So, yes, because my background might be like, I don't know how much fun my background would be. So I like skipped it somewhat. But yeah, so I work on, like, I mean, I'm primarily a mathematician. So I do research in math, exactly as Nick already mentioned. So homotopy theory, topology, category theory. And yeah, so what I try is formalization connections. I do try to like formalize some stuff in this area. So in particular, my dream is like formalize higher category theory, which is like very difficult. And this goes back to the stuff that Wowerski did, right? So his mistake came exactly from this world of higher category theory. So it would be interesting to formalize this because it's like notoriously difficult. And yeah, so this is some of the stuff that I work on. But I completely, so this is like, I guess one here. So this is like, I did mention this, right? This is exactly double categories in Quark. So this is something that I've worked on. So, which is like, or part of what I worked on. But I did not discuss in detail what I do because I didn't think it would be fun for this talk.
So will the slides be available?
Well, is that a question or?
That is a question. Yes.
They can be. Yes, of course. Why not?
Yep.
I mean, I don't
Okay.
know if you have a system for this. I don't know what happens if there's the website stays. If not, I can put it up online and then also share it.
I think
I
Bambode can. I think probably
yeah.
Bambode will know about this.
Yeah.
And there was a really interesting comment in the middle of your talk, which
Ah,
I think I should mention. It's
yes.
about so can we use this proof assistant while we are studying a new course? So not necessarily to do any research or to solve conjectures, but just say when we are learning a new material to compare our proofs with machine assisted proof.
I
And
mean,
then
this.
there were two comments sort of like it can be more reliable than GPTs. And if you are sort of getting a proof from this, let's say lean or something else, it might feel more ethical because you're also doing some work, except just entering your question in Chat GPT and getting the answer from them.
Yeah, I mean, this is. I mean, so I did not mention this. I don't know was a choice, but this is a very active area. So there's both people just integrating exactly proof assistance into their maybe exercises and so on. But more even advanced than this, there's this thing called lean verbose. And in Cork, there's also Cork waterproof, I think is the name, waterproof. And these are in some sense like some extensions of lean and Cork. And what they do is they allow some kind of limited controlled natural language. And so there are people now kind of designing courses based on this, where you have a course where you teach your material, like analysis or algebra, whatever. And then you have your exercises in the system where you can even like exactly do what the questioner suggests. You can build in hints. You can say, okay, like here's an exercise. Try to solve it. If you get stuck, you try for 5 minutes. You can't. Here, I'll give you a hint that shows up. Maybe you try like this. Maybe you assume first as an epsilon bigger than 0, and then start for next. So you can like exactly design exercises based on this. And this is already happening. There's a lot of like space and like pedagogy and like course design integrated with formalization. It's not exactly clear. This is like a little bit new. I mean, like teaching students is always you have to be careful what you do. So people are still figuring out how to do this, but there's definitely room for this, and there's a lot of people kind of looking into this. Yeah, well, there I'm reasonably optimistic that this will become some sort of standard. Because I mean, especially so this depends on like universities, but so a lot of these like bigger universities, you have these classes which are like massive, and getting feedback from a professor might be very difficult. But the cool thing about formalization is just instant feedback. Right? So these like when you like working like you interactive, right? Every step immediately tells you is it right or is it wrong, or what step, what assumptions have you, what step you need. And so it's exactly like almost like some kind of person standing there telling you, ah, this step is correct, and what you did is this, and here's what you need to do next to get to the result. So it's almost like a TA or something. So this is like, yeah, exactly. There's a lot of work, people thinking hard how to like make this work in an efficient way. But yeah, I didn't mention this in my slides. I should have here maybe included this. Was not a bad idea. Yeah.
There is a question about the strengths between Koch and Lin, but I think
Oh,
you
we
already answered
already
that.
answered that. Yeah.
Yeah, that's right. Yeah.
Maybe you had your question yourself, or no?
Any other question? Because I do have two questions for Nima.
Yes, exactly. Well, you can ask
uh,
why people think. Maybe they ask. Maybe
yeah.
they come back.
Yes. So I guess my inspiration will be from what people are saying about AI putting um, engineers out of jobs. My
Aha.
question is the combination. Will the combination of AI and these proof of system tools put mathematicians out of job or augment their work? How do you see this? Or could a
Yeah, I mean, this
section,
is like
which parts of
there
mathematics will
definitely
be most
are
included in this?
there definitely are lively debates about this. So if I think like I would say if you make significant progress on like the step two, but not on like step one at least, then there's definitely still a lot of room for mathematicians. Because I mean, you still need to like put input like a lot of math like by hand. And this will take like a long time. It's like the more advanced you get, also let's get technical and so on. So it's not that easy to like generate all of like maths, but still, I mean, then I would say it's probably like an eight, which like where if you have some kind of idea, you have some kind of proof construct, you can kind of give some rudimentary steps. So in a lean way, you would have stories. You can maybe write some proofs and some steps. You skip, you write some story, and then maybe you have some ML method, and then it fills in those like smaller steps or something like this. So then you would go much faster. Right? Like something like this could be feasible. That like it would be like an assistant which helps you and gets you to like a rigorous mathematics much faster than when you have to do it yourself. You have your idea, you want to write a paper, then you have to like sit down and figure out all the technical details, make sure all these like the codomains and domains match and whatever, and every number add up and so on. You don't have to do this anymore. You just put it in and it works out fine. If it really turns out, I mean, there's some people were like suggesting that this NLP is like super close and could be done. Then I don't know. I mean, it could be like suddenly make a significant progress where you suddenly can just input a lot of papers and get to like very quick, fast kind of level of like advanced mathematics being formalized and proven. Then it would be interesting. I mean, presumably, eventually, people will find a role for themselves in that space, but there could be like some kind of disruption, which would be at least temporarily kind of disturbing. So there's I think there's a range, and it's not easy to narrow it down. It depends on exactly what kind of progress, technical progress, is possible. I would say the same thing is for programmers. I don't think like all programmers will cease to exist, but it will be true that certain skills will become not that valuable because they will be replaced by like you have your AI something. It would just do the task for 10 programmers. You only need two, and the other eight kind of the work will be like automated or something. So there will be some disruption, and yeah, so the amount of disruption depends directly to the amount of progress that's possible.
Okay, so the jobs are safe for now, I would assume.
Yeah, I mean,
The
for
other
now,
question
the
is,
next, yeah, I think there's, yeah, I mean, there could be secret progress in labs that we don't know about, but to the like the actual knowledge that I have, yes, they're safe for now. I mean, it
yeah,
takes.
another cheeky follow-up is it which type of mathematician? Is he a number theorist? Is it who is more? Sorry, Rakvi.
Yeah.
Who is much closer to to putting to being put out of job with these tools?
I don't know if there's any. That's an interesting question. I never thought of this. Is there a specific area of math which is closer to getting
Yeah.
like kicked out? I don't
I
think
never,
so.
I yeah, I should say I never thought about this actually before you asked this question. So,
Yeah, it's just like,
so now
I
I'm
mean,
thinking about this.
Well, I think
Yeah.
it's safe to say you have like more than 20 years. I would think at least possibly with all these things, hopefully, the
yeah, but I mean,
development.
number theory is. I mean, the thing is, of course, if you think like number theory, of course, you have to ask yourself what you mean. Like number theory is a very broad field. There's analytic number theory, there's algebraic ones, and then some
As
that
well,
use
yeah.
modular forms, and some that use, I don't know, like some other methods. So it really depends. I would say it for now it's still. I mean, there's currently a project right by Kevin Buzzard trying to formalize Fermat's theorem. So it's like I would say a big number theory result. He himself has a projected timeline of like more than 5 years for that. Like, so I would say for now number theory is safe. For the other areas, it's the same. I mean, it's like despite all the progress, like most of research math is like very far away from being formalized. Like actual like cutting edge research that is being done by professors in math departments, that's like for most of it we're not even close. It's really like on the basic level, like bachelor level, some master level, that a lot of it is done. Maybe all, I don't know, but a lot. But the higher you go, also there's like way less people who actually have any idea what it is. Because it's really hard. I mean, you have like maybe like 20 experts who really understand this one property of like symplectic geometry or something, and you have to either convince one of them to like take a step and start formalizing, or I don't know, like it gets harder and harder to actually do it. The more refined it gets. So I don't know. I would say for now all areas of math are reasonably safe. I would not make a choice of which kind of PhD to do based on the probability of being formalized. But I would say if you want to do it, it's good to be aware and have some basic skills in this direction. Like just some literacy of like this how this works can be a useful skill beside whichever area of mathematics that you enjoy, I think.
This discussion reminded me of a movie. I'm not sure if you have seen this, or I think people in audience might recall this. So Charlie and Chocolate Factory. There's a movie.
Uh-huh.
I think the version in which Johnny Depp he was there. So the idea is, so Charlie, what happens to Charlie's father is robots take over. So his father worked in a company, and then robots take over, and then he loses his job. Okay, so
Mhm.
for some time, like his father is unemployed, unfortunately, so they are struggling to like keep the finances going and everything. But what
Mhm.
happens at the end of movie is his father is called back again to repair the robots. So
Aha. Yeah.
so I
Yeah.
think I don't think we will go out of jobs. Like human expertise is still needed.
Yeah, but this is
Uh,
I mean this is exactly the great example because there's a disruption, but then there's a change in skill. That's the
exactly.
change in.
Yes.
So you need
Yep.
like people need to adapt to it to some extent,
Yeah.
but it's not like there ceases to be a need for people to do stuff. But like the same way that there used to be in the beginning of my talk, there used to be computers. There were human beings who like sat down and did like prime number decompositions and like nobody does this anymore. These people are gone. But it's not like there's no people that now do just I don't know advanced data science or something. So one has to adapt to these technological advances, but I don't think there just ceases to be jobs. Yes, that's also my like I said, like the thing that can happen is if the technological progress happens too fast, there can be some disruption. There can be some people who like maybe they adapt just you don't have enough time to adapt.
Yeah.
So if you're a student now, it's perfect. But if you're, I don't know, a professor or like a researcher or a programmer doing this for 20 years, it's maybe harder to kind of adapt immediately to like these changes. You might need some time.
The
Yeah.
other side of this as well, I guess, with all these disruptive technologies is, as mathematics has become more specialized, and even the main branches have so many subfields, and there are so many little groups, small
Yes.
number of researchers working in these specialized thing. And if they stop or they retire, the knowledge is lost. How
Yeah.
could these tools actually be possibly used as well as a way of preserving mathematical knowledge over time? I would say, to
Yeah.
protect
Yeah. That's a
against
very interesting
fields being
perspective.
like yeah.
Yeah, I mean, this is one aspect. I mean, the other aspect of basic, but you say the same is like, so there's a lot of specialized knowledge, which makes collaborations sometimes very difficult. Where like three or four maybe can collaborate, but like 20 mathematicians can basically never collaborate on reasonable like scale because like the proofs are so different. But in formalization, they can, because when you formalize, you don't actually need to like know all the details. If the type checks at the end, it's correct. So you can really, and this is exactly how some of these projects work. So these, I mean, well, so these projects usually have, there's one or two people who are like experts, but then everybody can contribute, and there's like a lot of people kind of joining in and like maybe doing some parts. And it's not true that everybody needs to communicate all the details. If there's like one section of the proofs that where you know how to do it, you can just go and do it, and then if it type checks, it's correct. Everybody else can then use those lemmas immediately. So it kind of can help bridge some of these like very specialized branches and like help communication between those areas. This is like, and exactly. I mean, this I never followed this preservation part, but this is also true. It can also definitely help preserve and like help kind of keep those lemmas going and accessible for people. Interesting. Yeah.
Fantastic. Thank you for that. Any more questions on the thing? Because I have another question, maybe my last one.
Yeah, those are great questions. They make me think. That's good.
Okay, I don't see any. I think you already gone through all these other questions. I
Mhm.
guess I think Rakvi did before I joined. Um, okay, so this is more of a trying to. This is dangerous because I'm trying to give you a crystal ball
Okay.
with a bit of wishful thinking from you as
Uh-huh.
well. From all the existing open problems in mathematics, say the classical ones like the Riemann hypothesis and these things, which
Ah.
one do you think, or you would like, to have these tools help prove?
I mean, the one I would like is like I would like somewhere to compute the 100 groups of spheres, because I'm at heart I'm still a topologist, so that would be cool. But which one is the most realistic? I don't know. It's just like hard to. Like, I simply don't understand really how these like machine learning algorithms approach proofs, and what is easy. Like, what is an easy proof, but from the perspective of the machine, not from my perspective. I just don't really kind of understand this too well, so I can't comment on that. But what I would like is, there's something like this. So there's some computations. It would be cool if there would be some ML way to get more computations on this. That would be helpful. Yeah, for that, like the Riemann hypothesis, I think I have no idea how much like presumably you need a lot of like analysis and so on. And I would not know at all if that is something that like it's easier for machine learning methods than other stuff. It's a great question. Yeah, so yeah.
This,
I think I mean
this
there's
actually,
some. So I know some of these like I mean like LLM people, they are trying to make these lists of like questions and they benchmark and stuff. So they would be good to like they might have a sense what kind of areas of mathematics are easier in this benchmarking. So that would be good to look at. But I don't know if this is like benchmarking by area of math. I don't know if that's the thing.
mm,
That is too common. Just like there's usually just problems. You just have a list of problems and you just try to like see, okay, how likely is this to get right? I don't know if they're divided by areas yet.
mm.
But that's a good point. People should do this. I agree.
Thank you. I have another thing that, is there any other question, by the way? Yeah, I'm here. Yeah, exactly. So bombarding questions. Yeah. Could these tools also, because we've been talking about them obviously as a way of proving something. What about disproving, trying to find counter examples? Could we see tools like, these technologies, possibly also with increase of computational power that we are getting access, help in the future to refute some of the conjectures that are open.
I mean, a priori, every counterexample is just a proof of the negated statement. So it would like I think a priori there's no like fundamental difference, right? Like, uh, I've that so the question would be, is it? Yeah, I don't see any fundamental difference in that sense, right? You could just give the negated statement to the proof assistant and see if it can generate a proof for that.
Interesting.
Right? There's no other reason. There's no particular reason it shouldn't be able to do that. It should just be an existential statement, right? If you have your statement for all blah 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 is true, the negation sum exists so that the negated statement is true. And if you could like, if you have like some kind of algorithm that can like prove fancy stuff, you could try to give that negated statement that exists and see if it can generate a proof with the same kind of token, with the same kind of like logic. Yeah,
Yeah, thank you. So
that's
my
my
connection was
expectation.
not in there. Is there any other? I see something. There's a bit of latency from my end because I'm in the countryside. Is there any new on YouTube? We have questions coming both from YouTube and LinkedIn as well at the same time. So, is there any new question I can see here? Oh yeah, David. Well, it's not a question. I think it's more of an observation.
Yeah,
Yeah,
this is
it's very
exactly this is
interesting.
like one thing you can
Yeah,
imagine is exactly. I write and lean the statement of the Riemann hypothesis, and I have my very fancy AI, and it results in a type check proof. But the type check proof is like, I don't know, 13 million lines long or something. And then you have this. That's a very kind of interesting situation where you have a theorem, you have a proof, but nobody understands the proof. And then what do you do with this information? Like, what does it mean for the world and for mathematics and for us that we now have this correct statement? Because very often it is true that proofs have meaning. There's some intuition, like there's something that happens in the proof and it helps us understand what math is about in some sense. And we would like, if you really have this advanced AI thing, we would lose that. So there's like some space of what we do with this. So ideally, in that case, you would try to like then reconstruct human readable concepts out of this, right? So in some sense, the opposite of NLP, where like we go from natural languages to formalization, you would like the ability to like take a formalized proof and generate some kind of natural language proof out of it in a somewhat compact way, maybe. That's exactly also an area where like people are looking into, like going back to natural language. Yeah, so fortunately, we're not there yet. If that happens, I think this would be like a philosophically challenging situation in math. You had, for the first time, the proof of a very fancy statement that nobody can prove and like nobody else understands in detail for whatever
yeah.
reason.
This is what I guess maybe the guys at Google should be doing with AlphaGo.
Yeah,
Try-
and I'm sure they're trying something. I'm sure like all these people are trying stuff. It's just like it's just hard to like prove like open stuff with like existing formalizations. It's not easy. But I'm pretty sure they're interested in this.
So then that would create jobs, right, to make sense of these proofs then.
Yeah, in some sense. I mean, if you
That's
have
true.
some exactly, if you are an expert mathematician and
Yeah,
you have some experience with proof assistants, then exactly you could have jobs trying to like better interact with these and try to understand what they're saying. Exactly.
exactly.
Yeah, exactly.
So you become the arbitrator of the machine itself.
Yes.
Which is basically how many jobs already work. I mean, like if you are like a data scientist or something, you just don't make stuff up. You like try to like you write your algorithm,
Exactly.
and then
Yes.
you get the results, and then you exactly try to maybe calibrate, or maybe you think what the result, what it means, and so on. So that is an important part of many of these areas, right? So if computers are able to do stuff, then definitely mathematics would have to encounter and take that into account. Yeah,
Yeah,
that
I
is fine.
mean, to go back to the discussion that we were previously having, I don't think mathematicians are going anywhere. Maybe the like what exactly we do today would change or would evolve.
Exactly. Yeah, that's my
But
expectation too. Yeah.
I cannot imagine any world where, I mean, people who do research in basic sciences are not needed. I feel like they will always be needed. It's just that jobs will change a bit. Like teaching, like speaking from, let's say, teaching point of view, right? With all this chat GPT and lean and everything in classroom, I feel like our the calculus curriculum, the way we teach calculus in our undergrad courses right now, that what like they really need to evolve. Like for example, like some of the exercises or the exam questions that we ask our students, that
Mm-hmm.
can easily be solved by chat GPT these days.
Mm-hmm.
And up to like a good accuracy, like a calculus one class, for example.
Yeah, definitely. Bachelor, I think you can a lot of bachelor math you can do now, but with ChatGPT
Yeah.
and so on, quite like yeah.
So, but that can be a good thing because then we can really focus our teaching not on asking like these chat GPT questions, but to
Mm-hmm.
really teach concepts and ask maybe like more conceptual questions to
Mm-hmm.
students and say like, okay, you have this tool, maybe use this for your
Yeah,
computational questions. But
yeah. I mean, it's always a question what the correct and something do you like. Do you want them to replace just copy paste? But if they make suitable users, I agree. It could be definitely an
yeah,
effective tool. Yeah,
yeah,
definitely.
yeah, yeah.
It's really a question of like finding the right way.
This brings me to my final comment or a question for Nima. Um, how will all this affect stuff like a field medal? Say someone solves a problem using some of these tools.
Mm-hmm.
Say, for example, they didn't write the software itself that helped them to implement. Who should win the field medal for it? Just the mathematician who used the proof of system to prove it, or also the the person who helped create the whatever the new programming tool, the new implementation that helped the mathematician to prove the result for
So
which
this
they
is
were
with the
awarded the field medal.
assumption that like the proof was completed with some sort of AI step.
Yeah, yeah,
Yeah, that's a hard question. I don't know. I mean, in that case, yeah, it would. Yeah, I mean, I don't know. I would say probably this would not win a Fields medal if it was completed with some AI step. And then why give a
Can
Fields medal to
I
this person?
can I jump in? This is such an
Yeah,
interesting question. Sorry,
please.
sure.
but I mean, this is like more a question of collaboration then, right? And like, isn't
Yeah,
every research some sort of collaboration? Maybe like we are not collaborating with AI, but we do build upon previous work, right?
yeah.
So this is more a question of, and like who will win Fields Medal? I guess it's more of a community census.
Yeah, this is true. That's my point. I mean,
Yeah,
if there's like if there's some kind of great idea, some insight, some interesting definition, and you start proving stuff with it, and then there's some steps, and for the steps you use some AI. I think it's so fine. But if you have just a statement and then you run some AI algorithm and you prove it, then I don't think that should get a field now, right? Like, yeah. So make the analogy with collaboration. If I just propose a statement and somebody else proves it, some other human, I should not get a Fields medal for their proof. Right? I just proposed the statement. Right? If I do all the work and like I have some collaboration with other people and they help me understand some things, that's completely standard. Like all Fields medalists are like all the new ones I know, they all have collaborators. It's completely standard. But
yeah,
there's still an understanding that they did contribute something, that they have that some insight, that some idea that they're then in collaboration also refined and advanced and worked on, then yeah, that makes sense. So it kind of matters. The degree is kind of what matters here.
Yeah, that's very interesting because then I
Yeah,
think over the past few decades,
yeah,
we haven't seen these like joint. I don't actually remember any joint award in the field medals. It tends to be just one person be given for whatever specific. But
yeah,
now we're talking about collaboration with these all these tools and these things. But maybe they will probably adapt, similar to Nobel Prize of Physics, where it's like jointly awarded, I guess.
Yeah, I want to say, I was also thinking of the Nobel, because like I think Nobel is like actually common to award teams and groups, but in fields it's like still humans, like individuals. So I think they might need a change of culture, which we could see in the coming decades if this kind of AI thing becomes more prevalent. We'll see. There's a lot of these questions are also like cultural questions, institutional questions, and like a lot of institutions are very kind of conservative. They have their own kind of internal logic that they want to operate under, and so it's not always clear how things develop. But this is independent of the technology. It's like some kind of societal element. Yeah.
Yeah, there's a comment here. Wiles won the field medals.
Wild or
Fermat didn't.
Fermat didn't. Yes,
He was
indeed.
not alive.
Yes. But he probably would not have gotten the Fields Medal for like saying this is too large to fit into
Yeah,
this margins,
could
right?
actually, yeah, could lean. If maybe he was living in the wrong time, maybe he could nowadays with all these tools, he could have something to autocomplete his proof.
Yeah, I think probably not yet. Maybe if he like jumped to like 2050 or something and had the statement, then he could have probably autocompleted. So.
He wouldn't run out of space to run.
Yeah, yeah, exactly.
Okay, this has been really, really fantastic,
Yes.
Nima. Thank you so much for, I've learned so much for just listening to this, I'm sure all the audience. And thank you so much, Rakvi, as well, for hosting this as well. Yeah, so anyone, I don't see any question. Maybe I will just end the screen. But you guys, you can stay on the backstage if you wanted, just for us to
I think we should thank Nima again for a great talk.
Yeah. Everyone, let's thank Nima for this amazing talk and amazing insights that he's giving us. Thank you so much, Nima. Yeah, there's a bit of latency, I think, when people comment and put emojis on the chat or something. Okay, so I will end the stream. Thank you again, everyone who showed up. And yeah, this will be available for replay. Just use the same links that you are using right now. You should be able to replay. And I heard before someone asking about slides. If Nima is happy to make them available, I will distribute them across everybody who registered. So thank you again. Thank you, Nima. And thank you, guys. See